Good evening, everyone. I hope that everyone is doing great on this Monday afternoon. If you had a physics or government and politics test today, I hope that you did great on it. I am looking forward to hearing from my students about how they felt like they did on their first day of AP exams. And I hope that all of you did well also if you've already started testing. So today, we're going to be looking at for the AP Statistics exam, which we still have a little while. It is on May 22nd. It's a week from Friday, so we still have 2 full school weeks to review. And what we are going to be looking at today, we're really going to be focusing on every part of the formula sheet that was actually revised coming into this school year in order to match up with the new course exam description. So we're going to be going over that and altering it a little bit to reflect what's going to be on this year's AP exam, and also making some notes. And I'll post a link here in a minute. And it's a great place for you to sort of start your cheat sheet, I guess. There's definitely some things you would want to add in on top of what we're going to be talking about today. But definitely the formula sheet with some little notes on the side, some annotations is a great place to start. So that's what we're going to be looking at today. Follow us on social media. Also, TikTok is also available. TikTok, Twitter, Instagram, and YouTube for all of your AP exam needs going into this crazy few weeks. So the formula sheet is broken down sort of into 4 sections, and we are going to be looking at each of those 4 sections and then making some notes along the way. We're going to look at, first of all, descriptive statistics. Then we'll look at probability and distribution, the few different avenues of that. We'll look at sampling distributions and inferential statistics, which are very important. And then we'll quickly look at the tables, although I don't know that they're going to be that applicable this year. But we will glance at them and kind of review how to use those as well. Okay. So here is the formula sheet. So what I would recommend doing right now, if you're sitting at your desk with a printer, go to that website. I can post a link here in the chat and go ahead and hit Command P and print that guy out. Okay, so go ahead and print that out. That way you have it ready, and that can, again, it's kind of start your cheat sheet for you. There's definitely other things that we're not going to touch on today that you would want to have handy in order to make the best of your exam experience in the short amount of time that you have. But the formula sheet's definitely a good place to start because it does break down different sections of the course as well. Okay, so I'll give you all a few minutes to print that out, and then we will hop right in with descriptive statistics and start looking at those formulas, which ones are not necessary, which ones are necessary, and how we can sort of go through that process of kind of annotating it, I guess. Yes, this is the same one from the College Board website. I just, instead of remembering AP coronavirus updates.collegeboard.com or whatever it is, I just tiny URL'd it for you guys, make it a little bit easier. But it is the same one. It's the one they changed a little bit for this year, but it honestly looks the same. It's just formatted a little bit differently than the CED has it. Okay. So descriptive statistics. So this is the first thing you're going to see on the formula sheet. Okay. And if I'm just glancing at that, especially like as a student, I'm going to be kind of in a little bit of a panic mode because it looks to be a little bit overwhelming. Okay. The first one, X bar, that is just a formula for the mean of a given sample. And essentially what it is telling you to do is it's telling you to add up all of your data points and then divide by how many of them there are. That is absolutely all that formula is telling you to do. Okay, the sigma notation, if you've taken calculus and pre-cal, you've seen that and you're a little bit more familiar with it. If you're coming straight from Algebra 2 into stats, you probably haven't seen much of the sigma notation. That means you're going to add up all the values of X, and X are the data points. So you're going to add up all of your data points. You're going to divide by how many data points there were. Okay, nothing to be confusing about there. Okay. The formula just looks funny. Most of y'all know how to find the average as well. Katie, I don't think that you will be required to do these by hand because they are minimizing the amount of calculating that you have to do. I think there may be some calculations, but I don't think you're going to be required to do any fancy calculations like running a whole test. They could ask you to find the mean of maybe 6 data points. Something you could do with a 4-function calculator. That's what they've said. Anything you do with a 4-function calculator, that is possibly going to be a requirement. Anything that would require a graphing calculator, not so much. Okay, so a lot of these things we are going to mark off. But yeah, you could be asked to find the mean of 6 points, adding up 6 numbers and then dividing by 6. But that formula, don't be thrown off by it. That's all that it means. It's just finding the average. Now the other one, this is important, and it has a few little things to look at. So that is the form for linear regression. So y hat equals a plus bx. You also could write it as ax plus b if you want to. I like it better that way personally because it matches what we do in Algebra 1 with slope-intercept form, mx plus b. It just looks the same. They will accept it either way. But for some reason in stats, they want to put the y-intercept first and then the slope and the dependent variable. All right, now remember that you have to put the y hat. If you're asked to do something with regression and you're asked to write out an equation or whatever, your y has to have a hat with it because you are not actually finding the dependent variable. You are finding a prediction of the dependent variable. That is what a regression equation is for. It is for predicting the dependent variable based off of the independent variable, which we do know. So there's no hat on the x. The x is given to you, all right? It's the data point that you've collected, and then you're using that with the pattern from the other points, the slope and the y-intercept, to predict what the dependent variables might be, okay, based off of the regression model. All right, so y has a hat, always has a hat. If you're interpreting anything with regression, which to me would be the second aspect of my cheat sheet, I would have a formula sheet, and then I would have an interpretation sheet that interprets all the different things that we've interpreted, because you're going to be asked to do one of those. Okay. But if you're asked to interpret either a slope or a y-intercept, you have to have the word predicted on there in order to get full credit. That's always one of the 3 or 4 components they're grading you on. And the same with the y hat. Okay. It is a prediction. All of your y values that you get from a regression model are predicted y values. So, and then obviously the b would be the slope because it's with x, and then the a is the y-intercept, just like your initial value. Okay. The other 4 formulas in that section, I would mark them off. I highly, highly doubt they're going to ask you to find standard deviation or the R value. Honestly, for me, I find the R value or the slope or the y-intercept using the calculator anyways. I go and do linear regression with my data in L1 and L2 and make sure stat diagnostics are on. And then it gives me my R and it gives me my B. You might be asked to interpret one of those 2 things. I completely believe that's fair game, but I doubt you're going to be able to have to calculate those. I don't know if I've ever seen an AP statistics exam where you have to calculate R anyways. It's usually given in a computer output and you interpret it. I have seen some multiple choice where you interpret B or where you calculate B, but I've never seen calculating R. And again, put it in the calculator. Okay. You can download the TI-84 calculator emulator for Mac, Windows, or Chromebook and use that. It's just probably not going to be necessary, but if you had to, you could. Okay. I think it can make some problems easier. But yeah, mark those off. I don't think you're going to need those. Standard deviation, again, I would do first variable stats with L1 and L2. Now you might be asked to interpret standard deviation, and that would be another topic that you would want to do as part of your cheat sheet. So I don't want you to think that this is a complete cheat sheet. I would do one for interpretations as well. Standard deviation, R, slope and y-intercept, of course, our p-values and how to conclude based off of a p-value. Those are different things. I know my students have issues with that sometimes. Okay. So something else that I did, and I think you could fit this on the side of that section on your formula sheet, when you are asked to either compare or describe a distribution, here's the acronym that I use with my students. You might do something different, and that's totally fine. But you can CUSS the data. Those are the key things that are going to should cue you to jump into this cussing process. Okay, C, you're going to describe the center of the distribution. If it is symmetric, you can describe it using the mean. If it is skewed, you can describe it using the median. But then again, if it's symmetric, the mean and median should be pretty close to the same. Okay. U, unusual features. That most of the time is going to be in the form of an outlier. So if you have a box plot, you have an extra little dot. There's also that quick formula check. Q1 minus 1.5 IQR. That's pushing it to me on being able to do it by hand or with a 4-function calculator, but it is still there. So you might want to jot that down as well over there to the side. Doubt it comes up because it is a calculation that's more than a mental math to me, especially with a time crunch. But it's Q1 minus 1.5 IQR. That sets the lower bound for what is and is not an outlier. And then Q3 plus 1.5 IQR. I'll put that in the chat so you can write that down. So anything less than that, Q1 minus 1.5 IQR is an outlier. And anything more than this guy is an outlier. So those are your upper and lower bounds for outliers, non-outliers. Again, not a bad idea to jot that down there. If you had to prove that a point was an outlier, you could do that with a 4-function calculator if you had the Q1, Q3, and IQR. Okay, so maybe they give you that. In my opinion, it's a math exam, so there should be some sort of calculation, and that's something you could do pretty easily without a fancy calculator. So maybe that's something they do. So anyway, center, unusual features, describe the spread of the data. The easiest way for me is the range, or if you're given a computer output, IQR or standard deviation. If it is skewed, you should use one of the ranges, IQR or range. If it's symmetric, then you can use standard deviation. To me, range is always a good thing to use, the maximum minus the minimum. You can say the range is 7 minus 2 equals 5. The range is 5, and be very concise there. I would avoid saying that the data ranges from blank to blank. I've seen rubrics before where that's kind of, they bump you down a little bit. Spread is a noun, and I think they want you to describe it using a noun, such as the noun version of the form range. I'm definitely not an English teacher, but that's the best way I can think of describing that. I know last year there was kind of a catch on the rubric. Maybe it was 2 years ago, and I was like, but it's ranges from 2 to 7, but that was a partial credit, so I don't want you guys to fall into that. And then you need to describe the shape of the data. Never describe a box plot or a dot plot as approximately normal, unless if you want to check the empirical rule, which in 25 minutes or 15 minutes, you don't. Okay, so you can say it's roughly symmetric. If it has 2 modes, you could say bimodal. If it has, 2 clusters, you could say 2 clusters. I would maybe be careful saying bimodal if it has 2 humps and one hump is taller than the other, because then it's not really bimodal. It has 1 mode, but it has 2 clusters, because mode is the one that occurs the most often. Skewed right, skewed left. Remember, the tail is always in the direction of the skew. So if the tail is on the right-hand side of the graph, then it's skewed right. If the tail is on the left-hand side, it's skewed left. So just think, like, where is the tail at? That's the direction it's skewed to. So yeah, if you do those 4 things, can anybody put in the chat maybe one little detail that I haven't mentioned here that is always important in AP statistics? Context. Yes, Katie. Whoever your AP statistics teacher is awesome. Okay. So always, 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 your answer should be in context of the problem. I've seen rubrics before where context literally is, you could say the median is about 5 inches, and then everything else is just, there's no outliers. The spread is 4. The shape is roughly symmetric. But you said inches that one time, then you got context. I would do more than that. I wouldn't try to be like, well, I said inches. I would put context in all 4 parts of it and make sure that if anybody were reading the one thing you have, that you were sure on what you had. Okay. That, they had no clue what the problem was about, but they could read your response and make sense of it. Okay. So context, context, context. Can't stress that enough. No matter what you're interpreting or describing, it has to have context. Every single rubric will have that on it. Okay. All right. And here's a little sketch for skewed left and skewed right. So the first one, my little bar is in the way. Okay. So our first one is skewed left because the tail is on the left-hand side. The other one's skewed right because the tail is on the right-hand side. Also, something to keep in mind, and you can see it with this little picture here, is that the mean is always going to be pulled towards the tail. So whenever it's skewed right, the mean is greater than the median. And when it's skewed left, the mean is less than the median because the mean is always to the direction of the tail. The median is always between the top of the hump, which is the mode, and the tail. Okay. So make note of that too, maybe on the side there. Mean goes the direction of the tail. You could sketch out those 2 things. I could see that being a question like a part B, part A being describe a distribution off of a frequency chart. And then part B, say, is the mean more or less than the median, and explain why. Okay. And if you've got that concept, then you're good to go. A and B are super easy. If I were putting money on what would be on the 2020 AP statistics exam, there's two things I would be really sure on, maybe 3. And one of those is being asked to compare or describe a distribution. In other words, to CUSS the data. Okay. If you can do that, I think you're going to get good points off that problem. That's one of those crux problems, that being able to conclude a hypothesis test by comparing the p-value to alpha, and then knowing that observational, experimental, to me, that's the golden rule of statistics. If it's experimental, you have, you may could write this on your formula sheet as well. Experimental has assigned treatments, randomly assigned treatments. And then that leads you to make a cause and effect relationship. Okay. So that is the golden rule of statistics, cussing data, and then interpreting a p-value. Well, comparing a p-value to the alpha in order to conclude a hypothesis test. Those are my big 3 that I'm pretty sure are going to be on there. A lot of other things are fair game, might be on there, maybe not. So we'll see. Okay. Any questions on descriptive statistics? I know the cussing the data is not on the formula sheet, but it's just really important. Okay. I would write context on your formula sheet and your cheat sheet like 80 bagillion times. So you're like, oh, how do I do this? Context. Oh, yeah, I got to do context. I do not know where the answers to those are, Shruti. I have looked. Let me open up a new tab just to make sure it's the one I'm thinking of. Yes, I have not seen that, the answer to that. Katie, you said student samples. Are there student samples to that particular question available online? Okay. Somebody did say something in our Slack about student samples for STEM subjects. So you're right. There may be student samples out there, and one of those would be a 4. I want to know if they're still grading on the scale of 1 to 4, and I've been trying to figure that out over the past few days. That's been my mission. But that particular question, any example that I've used on my streams has been pretty close to in line with the example they have. Okay. Yeah, they do have student samples for previous AP Stats exams. I just don't know about that one sample there that's written like this year. Yeah, that might be from a teacher group that people are working together. I'm in a few of those as well. People might have put that together based off of how previous AP exams were graded. So yeah, I think the last 2 or 3 weeks I've done, I called them COVID style free response questions. And I looked at that one to kind of make sure I was making up questions on the same ideas. So if you want to do that, you can go back. It should be bookmarked on those streams as well. And I think if you're in the Cram Pass, I'm sure there's some of those as well in the Cram Pass streams also. So yeah, look into those. That's a good question though, because that's one of the few on the AP website that we can look at and know what the test is going to look like. And it does line up with things that we've been doing at Fiveable and things that I've seen at other sources too. So I think we're all kind of on the same page. All right, so moving on, the next section is on probability and distribution, or probability distributions. So you have these two formulas here, which to me were always very valuable on the multiple choice section, but I mean, you never know, they could throw something on free response. So this first formula is the probability of OR, all right? And the way you're going to find an OR probability is you're going to add up the two individual probabilities. So the probability of the first event plus the probability of the second event, and then subtract the overlap. So subtract the probability of both of them occurring at the same time. That could be done pretty easily on without much calculator help in a if it were a frequency distribution where all the totals are 1.0. So you have a bunch of decimals. You could add up two decimals, two totals, probability of A, probability of B, one horizontal, one vertical, and then subtract the one cell where they overlap. And that would give you the probability of the and of the or, A or B. Okay, so not much calculation involved there. You could do that. But then from a two-way table, you're adding up the two individual probabilities and then subtracting the overlap. That's what that formula is for. The next formula is for conditional probability. That comes into play a lot when you have independence. I have seen a question of 2 or 3 of the mock exams I've looked at from other teachers have brought up independence. So I think that's pretty likely to be on there. And what you're going to do for independence is you're going to compare the probability of A given B. So if you're doing a two-way table, that's you're going to just look at row B, okay, whatever event B is, just look at that row or that column, and it makes your denominator smaller. And then you're going to compare that to the probability of just A. So if the probability of A is equal to the probability of A given B, that means they're independent. I'll type that up for you guys. So you can see it, and you can add that to the side here as well. Okay, so from a two-way table, those are pretty easy to find, and you would be calculating those or looking at those and then comparing them. If they're equal, then those two events are independent. They're not affecting each other. Basically, you're just as likely to have event A occur as you are to have event A occur when B has already occurred. They're no different. Okay, the proportions are the same. Okay, also those formulas can be used backwards. So sometimes, and I've seen this a lot on free response, is that you'll be given probability of B and then A and B, and then be asked to find the probability of A and B. Okay, so you'd be given the denominator and then the answer, and be asked to find this one. And a little cross multiplication, backwards math, and you can solve it. Okay, so that is how you would do that. And if you want to find the and probability of A and B, you just multiply A, probability of A, times the probability of B if A and B are independent, which you can kind of make sense here, right? Because if this is equal to the probability of A, then A times B cross multiply equals the and. I think you're more likely to see these themes from a two-way table where you can write out a fraction and be done, as opposed to plugging in decimals and working backwards and multiplying. I think that's kind of some hairy calculations for what we are expecting out of the exam. I would be prepared to calculate and or conditional or a probability of A or B from a two-way table. We have streams on that back from a few weeks ago and also several months ago. But I know that in the Cram Pass, we knocked that out as well. And then I did a free stream on it also. If you're not part of the Cram Pass, you can go back and watch that. Free stream on two-way tables and tree diagrams. Okay. That was a fun stream to do. Fun for me, probably maybe not for y'all. All right. So the next part of probability distributions is when you have a discrete random variable X, it has how you would calculate the mean and the standard deviation. The mean is the same as the expected value. Those two things mean they're the same definition, just different words. Basically, you multiply the value, like if your values are of your random variable are 0, 1, and 2, you would multiply by 0 times the probability of 0 happening, 1 times the probability of 1 happening, and 2 times the probability of 2 happening, and then add those three numbers up. And that would be the mean. That would be what the average expected value of whatever the random variable is. Okay. Standard deviation, again, I don't think that's going to be on there, but if it were, I would do it on the calculator. L1 is going to be your values, 0, 1, 2, 3, 4. L2 is the probabilities of those things occurring. And then you're going to run your first variable stats. L1 is going to be your data set. That's your 0, 1, 2, 3, whatever your values are. And then your frequency list is L2. Normally, we just leave frequency list 0. But when we have a probability distribution that we're calculating those things for, our L2 is our frequency list, basically saying that, 0 is occurring 0.1 times and 2 is occurring 0.4 times and whatever the other probabilities are. Don't think that's going to come up. Expected value could possibly come up, but it would be an easy calculation, and knowing the formula there, you can do that. Usually looking at a table kind of like this, and you multiply this times what's below it, the next one times what's below it, and add up all your products. Make sure you show your work if you have to do that. It's simple calculations, and in the past, you could do it all at once and just write out the answer, but show what you got and how you calculated it, because showing work is one of the things that they want you to do. I've seen people get questions right on that, and I know that they did it correctly, because you can't just randomly get 0.15, or whatever the answer is, and then but they didn't show the work, so they didn't get full credit. When you're doing this, it will not give you the sample. When you use the frequency list as L2, the S of X will be blank. It'll just show the sigma X on the calculator. So you would use the population standard deviation. So that makes it easy on that one. You don't have to know which one to use. It would be the sigma on this one. All right. All right, next one is binomial. You got that fancy formula there. And your formula for mean is really easy. It's just n times p. Your formula for standard deviation is n times p times 1 minus p, and then take the square root of it. N being the number of trials, p being the probability of succeeding. So that the mean and standard deviation are easy. Calculating the binomial formula is not. We've always done binomial PDF or CDF on the calculator, which now is they've pretty much said that's not going to happen. So what I would make note of in the section with binomial is, how do we know if a probability is going to follow a binomial distribution? Okay, how do we know that that random variable is binomial? Yes, the first one is binary. So I always kind of break down the word binomial. That's the 4 parts. It is binary. It has a clear success and failure. Nom, kind of like number. You have a fixed number of trials. That's really important, because the next part, that's not true. Each trial is independent of each other, and all trials are equally likely to occur. So you can see the word binomial there kind of made out, and it gives you the 4 qualifications for binomial. I could 100% see them giving you a distribution and saying, what type of distribution is this and why? Explain. And you have to say it's binomial because yada, 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 or it's geometric because yada, yada, yada. Okay. So knowing those 4 things, if you were going to use binomial CDF in the past, sometimes you did have to clarify how you could use that. So you had to state, kind of like your conditions. When you do inference, you have to do conditions to make sure that you can actually perform that inference. So it's sort of the same way here. If you're going to do binomial CDF in the calculator, you have to know why it's binomial. So make sure you have those 4 qualifications there for binomial. Okay. And geometric, it's a little bit different, but it's very similar. Okay, so there's your formulas. Again, we normally have used geometric CDF or PDF. Don't think that's going to show up. But it could, I guess, possibly just to plug into the formula, 1 minus P, and then raise the formula X minus 1 times P. Maybe, I don't know. Maybe not actually calculate it, but just plug it into the right formula. So it's the definition of a geometric distribution is very similar. So it still has a clear success and failure. It's still binomial. It is still, trials are independent of each other and they're all likely to occur. But with geometric, it is not a fixed number of trials. You are finding the probability of something happening at a certain trial. What's the probability of drawing a red marble on exactly the 5th trial? Okay. Or not drawing a red marble until at least the 5th attempt. You could do that as well. But you're basically doing the probability of something happening up until a point where it stops. Okay. So it doesn't tell you you're drawing out a marble 20 times. It says you're doing it until you get a red marble. Okay, that would be geometric. So similar there. It's one of those tough concepts. That's one I'm always concerned about for my students going into the AP exam is binomial and geometric, even when they did have a calculator. Okay. Any questions on the probability section before we hop into sampling distributions and inference? Any questions? Anything I need to hop back to? I'll be more than happy to. All right, let's keeping on and look at sampling distributions and inferential statistics. This is where the moneymaker is. Now, when you're doing inference, okay, when you're calculating a p-value, you are calculating the probability of something happening on that sampling distribution. Okay, sampling distributions are a direct tie-in to inference. When you are checking the normal condition, you are checking that the appropriate sampling distribution is normal. That's really important, I think, on this exam to be a little bit more precise on what, because they might ask you, they might say, in order to perform this test, you have to make sure that your sample size is at least 30. Explain why this test is important. Okay, you would be explaining that that is important. You can't just say normal. Okay, that's typically what we've done in the past. But you have to make sure that the sample size is greater than or equal to 30 so that the sampling distribution of size n is approximately normal, and we can use the normal curve to calculate p-values, z-scores, t-scores, whatever we're looking at. Okay, so it has to be that the sampling distribution is normal. That's why it's important. That p-value is the probability of getting our unique sample if the HO is true. That's what the p-value is. That's what that interpretation is. We always think, oh, well, p is low, we drop the HO. That's what we kind of revert back to when we think of p-value. But the definition itself of that p-value is the probability of obtaining our unique sample that we have from our data set, given that, or if the HO is true. Two proportions are actually equal. If they're actually equal, what was the probability of me getting my unique sample where they were a little bit different? Okay. And that's based off of the sampling distribution. I think that's important. Okay, so standardized test statistic. If you have to calculate a Z or a T score, that is the formula you would use. I always think it's easier to think about it as observed, which is what you have from your sample statistic, minus what you would expect, which is your population parameter, and that's all divided by the standard deviation. Okay, so that's the way that I would look at that. Okay, so another little note here. This should also be in your interpretation cheat sheet, but it's just worth looking at now that we're looking at z-scores and t-scores. The z-score is looking at how many standard deviations our particular value is either above or below the mean. That's what the definition is. People get the definition or the interpretation for z-score and standard deviations backwards a lot. Standard deviations does not have a direction. Standard deviation is a magnitude. You're only measuring like a distance, whereas z-score is a distance, but also in a particular direction. Are you greater than the mean if you have a positive z-score? Are you less than the mean if you have a negative z-score? Okay, so make sure you include context and direction if you're asked to interpret a z-score. It has two parts. You have your statistic from your sample. That is your point estimate. That's the one number you have that you're using to estimate what the population parameter is. Well, my sample is proportion is 0.54, so I'm thinking that my population is pretty close to that. Okay, or my mean of my class is 75, so the nationwide average is probably also pretty close to 75. Okay, so that's the point estimate. That's your sample statistic. It's either your mean, your x-bar mean, or your p-hat from your one sample. And then you have your margin of error. That is what you're adding and subtracting to that middle point. Okay, one of the mock exams that I had my students do, that was one of the things it asked them to do. It gave them the interval, and it said, what's the point estimate and the margin of error? Quick four-function calculator, you can solve that. Find the number in the middle of those two endpoints to be the point estimate. How much are we adding and subtracting to get to those endpoints is your margin of error. Okay, no fancy statistics calculator needed. So that is how we would go about calculating that. I would make note that those are the two aspects of the confidence interval. The formula sheet doesn't list them out that way. It breaks the margin of error down into the two parts of it, the standard error and the critical value. But together, those things make the margin of error. And the point estimate is the sample statistic, whichever that is. Another thing you could jot down is that the larger your sample size is, that's going to make your margin of error go down. A larger sample is going to make your critical value go down. It's going to make that become smaller. And then also it's going to make the standard error, your standard deviation go down. Okay. Remember, larger sample size, that standard deviation of our sampling distribution shrinks in. Okay. All right. I think that's a really important part. I could see some calculations based off of what we just talked about. And simple calculations too. Nothing that requires a TI-84. You can do it with a four function in, half a minute, 30 seconds. Okay, chi squared statistic. What do you think I'm going to do with this guy? Not using it, okay? It's kind of, yes, ignore. It's kind of a shame because chi squared are used in the real world in statistics a lot. So is linear regression inference. It's used a whole lot. You might have even seen some of that with the data that's being thrown at us with the COVID-19 outbreak. There's a lot of regression statistics being thrown at us. And some of that required some inference procedures. And we're kind of skipping that. But yeah, so no need to worry about chi squared for this year's test. So that part on the formula sheet, if you printed it out, just X through it. It's not distracting you. It's not there. Okay. So then we have our parameters of our different types of tests. So first of all, it gives us all of the formulas for calculating the mean and the standard deviation when we're dealing with proportions. Okay, so if I have one population, okay, p hat is going to be my middle. That's going to be my point estimate. Okay, and then we're adding and subtracting this times our critical value. Okay, so our sampling distribution follows these two. And then this is the formula. Notice it's the same. The only thing we're doing differently is that if we're just given a sample, we don't know the p-value, so we use p-hat. All right. Same thing when there's two populations. Okay. Pretty crazy formulas. I don't see them being pulled out this year because the standard deviation is kind of crazy. Okay, I wouldn't want to do square root of 2 fractions added up if I didn't have a calculator handy. You could be asked to calculate the mean of a sampling distribution given the 2 population proportions. You'd subtract them. That's pretty easy. I mean, you can do that, no problem. One population has a mean of or has a proportion of 0.6, and the other population has a proportion of 0.55. What is the mean of the sampling distribution of the difference of the 2 proportions? 0.6 minus 0.55 equals 0.05. Easy calculation there. It's right there on the formula sheet, though. The standard deviations, I can't imagine going that much more difficult, or that being this difficult. So if you are assuming that the 2 proportions are equal, which is what you do when you do a hypothesis test, okay, then you're going to use the combined proportion, okay, which basically you just take the total, add up your 2 samples, add up your 2 successes, divide them to be one number instead of doing it this way. When you're doing confidence interval, you don't necessarily assume that the 2 are equal, so then you would use this formula. A little bit of difference there. That's kind of strange, but that is how you would go about doing that. Okay. All right. Now, I would also write this out. I would write out your conditions for doing proportions. Now, notice I made note there. Proportions, you're doing the z-score or a z-interval or a z-test. That's everything's z when you're doing proportions. All right, our first condition is random. Make sure each sample is random in some way. Quote the problem if you have to. 30 randomly chosen employees. 30 randomly chosen employees. Just quote it. If it's an experiment, you have to note that it is randomly assigned. That's the whole idea behind an experiment. Okay. That's necessary to ensure that our sample did not occur due to bias. So we didn't get this magical sample that makes us doubt what the statistical claim was because we just asked the people we were friends with that had the same opinion as us or whatever. Okay, so it has to be a random sample to make sure that we have a true representation of our population. Our sample's a little picture. We ask them questions or take their averages, and that helps us make inference about the big picture. If we only ask our friends, then all we can make inference about is the population of our friends, which we probably ask most of them. Okay, and it doesn't really tell us much. So yeah, we have to make sure that our sample is random because it ensures that we are getting a true representation of our population and we can make that inference jump from sample to population. All right, independent. That is actually not necessary when you have a completely randomized design due to randomized treatment. So if you have an experimental design problem, it is not necessary to check the independence. There's been a lot of debate on that online. But I've seen several places from very trustworthy people that it does not have to be checked. Now, if it is not an experimental study, if it's an observational study and you do not have randomized treatments assigned, then you basically just have to state that it's reasonable to believe that our population is at least 10 times our sample size. Always include context. That is necessary because we need to know that we are sampling. Well, we're sampling without replacement. We need to know that is not going to have much impact on our sample. Yes, sure, my probability of choosing John on the second draw is a little bit different than what it was the first draw. But since our population is so much bigger than our sample, it's not much of an impact. It's such a small impact that it's not going to really minimize things. Okay, and then 3, normal. When you are doing proportions, that is the large counts condition, not central limit theorem. So NP greater than or equal to 10 and N1 minus P greater than or equal to 10. Remember, that is to ensure that the sampling distribution is approximately normal. That is the distribution you're checking to be approximately normal. The sampling distribution for whatever we're trying to estimate. The difference in proportions, the true population proportion, sampling distribution of size 3, whatever it may be. Okay. If you're doing confidence intervals there, you use p-hat. If you're doing the hypothesis test, you're going to use the P that's in the hoe. And if you're doing 2 samples, you have to check both samples. N1, P1 greater than or equal to 10, and so on and so forth. All right. A lot to write down there, but those conditions are necessary. You will probably have a condition problem somewhere on your exam. All right, so jumping over to means now. So we have, if we take all of our X bars and average those together, that will give us the true population mean. And then you have your formula for standard deviation. For a sampling distribution, you just divide by the square root of m. And then the same thing for the 2 populations. Standard error is nothing too tricky there, okay? Take the standard deviation of your sample statistic, divide by the square root of n, or sample standard deviation for your 2 populations, same thing, okay? You can notice here you're kind of finding the variances. You're squaring them and adding them up and taking the square root. So you have to take the standard deviation and square them, add them up, and then take the square root, because you can't just add standard deviations and you can't subtract them. We subtract the means, but for standard deviations, we have to do Pythagorean theorem to get there. Talked about that last week, okay? All right, and then our conditions. Means is always t-scores or t-intervals or t-tests. So you might be asked, which test would you want to run here to show, to test if the difference in these 2 means are actually different. And if it's a test, you would do, a 2-sample t-test in that case. Okay, just make sure you know proportions go with z, means go with t. And then with t-test, you have degrees of freedom, which is kind of a little caveat there. Random, make sure each sample is random in some way, same exact thing as before. Know why it's important that you have random, because it allows you to make a scope of inference bigger than just our friend group, or bigger than just the volunteers who went to the baseball game or whatever it may be. Independent, same idea there. Normal, first thing you want to check is the central limit theorem. If n is greater than or equal to 30, your sampling distribution is normal, is approximately normal. You can proceed. If that doesn't work, you can check to see if the populations, either 1 or 2, if it's a 2 sample, are normally distributed. If the population is normally distributed, then the sampling distribution of size 5 or 30 or whatever would be normally distributed. And lastly, if you don't have either one of those 2 things, you can have a box plot of your data or some data representation. Make sure that it doesn't have really strong skewness or apparent outliers. Okay, and do one of those 2 things, then you're good. Okay, and then I made a note there again. Remember, we're checking normal to be sure that the sampling distribution of whatever our given sample size is approximately normal. That's what allows us to calculate the p-values. The p-value is a normal CDF of a sampling distribution, or a normal or a t-CDF of a sampling distribution. That's what those p-values are pulling things off of, is a sampling distribution. It just does it all for you at once, as opposed to taking your mean, calculating your mean and your standard deviation, and then going to normal CDF and calculating the probability. You would get the same answers. Okay. Sampling distributions for linear regression. Not using it this year. That's unit 9. You can exit off. Don't be distracted by it. We don't need it. It's honestly a very small portion of the exam on other years anyways. And in the past, I've actually skipped it. And I don't think that it's hurt my students that much. But this year, it's not going to be on there at all. So no need to tie up on that. All right, our tables. I'm going to swap what I'm sharing, and I'm going to share the tables, and we'll just chat about those for a minute. Don't think they're going to be that vital. So this is the z-score chart. So you have the first chart is when the z-score is less than the mean. All right. So you would calculate your z-score based off of your observed, expected, and standard deviation. And then you would match your z-score up. Negative 3.44 has a p-value of 0.0003. Basically, there's less than a 1% chance of getting that value or less. The tables are always based off of being that particular value or less. The second page is for numbers greater than, so positive z-scores, greater than the mean. Now, if you were asked to find the probability of getting this value or more, you would find the z-score from the table and then subtract it from 1. So if you needed a probability that was moving to the right instead of the left, you would just subtract from 1. Most of you all probably use normal CDF or, a 2-prop Z or 2-prop Z tests instead, or 1-prop Z test, depending on the test. Probably don't use the charts anyways, but they're there. That's how they work. The next one is T-star. You have to do your degrees of freedom, which varies depending on the test. If it's a 1-sample t-test, you take the sample size and subtract 1. If it's 2-sample, there's a few different ways you can go. Usually the calculator does it for you. And basically you'll do that. Whatever your confidence level is, and then you can sort of calculate it from there. Okay. And a high t-score or a z-score generally reflects a low p-value. So there's that. And then after that, you have chi-squared, which we are not doing this year. Okay. So that's how z and t-score chart works. I don't think they're going to be that vital, but, they are there. Yes. Did I answer your question there, Shruti, about if it's more than if it's greater than the mean, you subtract it from 1? Sorry, I was on a different tab there. So yeah, if you were looking for this probability, the probability of this value or greater, you would take the z-score from the table and subtract from 1. That is correct. Any density curve always has a probability of 1 total. Okay. Yes, if you're doing it from normal CDF on your calculator, you set the lower and the upper endpoints, so you don't have to worry about subtracting from 1. The only time you would subtract from 1 with the calculator, if you're doing a TI-84, is if you're doing binomial or geometric. It will not let you set the lower and upper endpoints. TI-Inspire does. I don't know why. It's really frustrating. But yeah, normal CDF, you just tell it what the lower limit is and the upper limit is. And you tell it what the mean and the standard deviation is. So therefore, you don't even have to calculate the z-score. Okay, it does it all for you. Okay. Any questions? I think that was the last of my slides. Yes. Any questions real quick before we hop off of here regarding the formula sheet or anything else from the test? Maybe I can help you out. All right. I guess we're good. So hope you all have a good rest of your week, and I hope you're all staying safe. And okay, got some questions. Here we go. Can our cheat sheet be online, or does it have to be printed? I think it can be online. I think you can have a separate tab opened up, but I'm not 100% sure on that. I think it would be better to have it printed so you're not constantly changing tabs. Okay, you used online notes for AP Gov exam today. How was the uploading process on the AP government exam, Katie? Was it good, bad? Okay, so you copied and pasted. It was easy, no lag. Good. I know there's some issues with the physics exam this morning. Yeah, surprisingly. So hopefully they get bugs worked out before AP Stats. We were the last exam on the last day. So hopefully all the bugs are worked out, and we don't have to suffer like the physics people did this morning. Hopefully it just keeps getting better. Yeah. All right, there's another thing. What is something we should be expected to see on the test? So the big 3 things I would say. Number 1, identifying if a study is observational or experimental. What type of study is this and why? To me, that's the golden rule of statistics because it leads you to establishing cause and effect or not. The second thing is describing a distribution, cussing the data. So you would test the demo during the 12th. Yeah. Okay. I went over the demo like 8 times now, it seems like. And it seems to be good, but we'll see. But yeah, going over the demo at 12. Yeah, probability is going to be on there. I think the most likely form of probability is probably like a two-way table. But I mean, remember, like normal calculations are that's probability. Okay, normal CDF, you were calculating a probability of something. But two-way tables, tree diagrams, all those things, I would look back over the next, you got a week and a half. So I would focus on those if that's something you're not comfortable with. And so I said that those two, compare, describe a distribution, that's cussing the data. And then the third thing is, if you're going to be, I think you'll be given a p-value and ask how would you conclude. P is low, you drop the hoe, which means there is not convincing evidence of the, or if you drop the hoe, there is convincing evidence of the alternative hypothesis, always in context. If the P is not low enough, you don't drop the hoe, there is not convincing evidence of the alternate. So those are my big three. I would expect to see questions almost identical to those three. So yeah. All right, guys, y'all have a good week. Good luck on your exam. Again, next week we'll be back for a Q&A session, a little bit more like what we did just now. I'll come up with some questions for us to look at, and I will see you all then. Thanks for joining.